All right, here we go. So Unit 8 really is just more energy. Specifically, we're going to focus on two things. 8.1 and 8.2 are both about conservation of energy. And then 8.3 is about what are called potential graphs, potential energy graphs. Okay. So today we're going to focus on conservation of energy. We're specifically going to deal with problems that have no elastic potential energy. There's a really big new thing in this. The big thing that you're going to get that's new this year is a lot of these problems, for whatever reason, these conservation of energy problems, a lot of them deal with non-uniform circular motion. Okay, and if you haven't already, you will see a little bit of this in a lab that we're going to do where you whirl your force probe around. Okay, so that's sort of where this is coming from. All right, so anyway, so a lot of the first chunk here is review, just to kind of get you back up to speed. So remember, when you deal with energy, two types of forces, conservative forces and non-conservative forces. Remember, conservative forces are gravity, elastic, spring or something, electrical forces, chemical forces. These are all forces that are responsible for a form of potential energy. Okay, and non-conservative forces is basically anything else. All right. So last chapter, we talked about the fact that conservative forces are forces in which the work done by the force on an object as it moves between 2 points doesn't depend on the path it takes. Okay. Sometimes books give this definition, which I don't like quite as well, which says the work done by the force on a closed path is always zero. All right. So anyway, we talked about this last time, right? We talked about the fact that the gravity is conservative, right? Because no matter how you get from point A to point B, you're still going to have the same change in gravitational potential energy, right? So whether Sally climbs down a ladder or slides down a slide, she's still going to have the same change in height, as a result, the same change in gravitational potential energy, and therefore the same work done by gravity, right? Okay, so I know I'm plowing through this because we've done it before, but I just want to refresh your memory. All right, so conservative forces are conservative because the work done by that force between 2 points doesn't depend on the path. All right, and we talked last time about the fact that the force of friction was not conservative, right? Because if you've got a box and you slide it from here to here, then you're, if you just slide it in a straight line, then the work would just be the force that friction exerts times your displacement, right? But if you do this, then your friction is always opposing your motion, right? So you're going to have your force over a larger distance, right? So the work done by friction there would be larger. Okay? So anyway, I don't know why I'm going through this all. We've done it before. I just didn't want to delete the slides, if I'm being honest with you. So I'm sorry I'm wasting your time. Here we go. All right. Oh, more review. Okay. Do we care about any of this here? I think the big thing that we need to know is this. When a conservative force, okay, so this is important. I don't think I stressed this last time. All right, so if a conservative force does work, it doesn't actually change the total energy. The only thing that it's doing is it's converting energy to or from potential energy, okay? If you've got positive work done by a conservative force, it means that you're losing potential energy and gaining some other form of energy. Here it says KE, but it could be transferring the energy to some other object. Similarly, if a conservative force does negative work, it means that you're gaining potential energy in some fashion. Okay. We should also, I guess, review how it's possible for a force to do no work. All right. So remember, the only way that a force can do work is if the object is moving and the direction of motion cannot be perpendicular to the direction of the force. Okay, so what this means for us is that, well, so we talked about this last time, right? So if you've got a box sliding down a ramp, oh, it's the worst box ever, then your motion is this way, your normal force is this way, those are perpendicular. So when you've got a sliding object, your normal force doesn't do work, right? Because your normal force is always perpendicular to the motion. Okay. All right, and this chapter, because we're focusing specifically on what I call conservation of energy problems, in this chapter, we will not have non-conservative forces doing work, okay? Because that would change your total energy. That's chapter 9, okay? So, all right, so the law of conservation of energy says the following. If the only force doing work on an object, or the only forces doing work on an object, are conservative forces, then the total energy stays the same, okay? So that's how all of the problems in Chapter 8 are going to have this property. The forces on the object will either be conservative, or if they are non-conservative, they will not be doing work because the non-conservative forces will always be perpendicular to the direction of motion, okay? So, as a quick reminder, what do we mean when we say total energy? Total energy is just the sum of all the types of energy. For us, total energy is usually going to be kinetic energy, rotational kinetic energy, which also comes later this year, gravitational potential energy, and elastic potential energy. To be clear, remember, when we talk about the total energy, we're talking about the total energy at an instant, okay? And so this little example here kind of highlights this. So Roy fires a water balloon at Sally. When the balloon is at the top of the path, at that instant, you're going to have gravitational potential energy because the balloon is up in the air, kinetic energy because it's moving, so the total energy at that instant would be 50 joules. All right? All right, so here's just another statement of the law of conservation of energy. Energy cannot be created or destroyed. It can only be converted from one form to another or passed from one object to another. So what that means is, as long as energy is not passed from one object to another, in other words, if the non-conservative forces don't do work, then the total energy will remain constant. Okay? Skate park, I showed you guys this last year in honors. I'm not going to do that again. I'm going to, oops, I didn't need to do that. Here we go. All right, so 2 examples. The first one, simple, just a quick refresher in how you solve these problems. And then the next one is the real deal. All right, so what if we slid a box down a frictionless ramp that was 3 meters tall? So you've got a ramp, 3 meters tall. Doesn't tell us how long it is, but we're going to slide a box down the ramp. Okay? So we're going to assume it starts at rest. So up at the top here, the velocity is 0. The height of the box is 3 meters. And the question is, when the box gets to the bottom, what's the velocity? And so the idea is, oh, well, when it gets to the bottom, your height is 0, right? So to solve this, what we're going to do is we're going to recognize that we've got 2 points. We've got point A at the top of the hill, point B at the top of the hill. As the box slides, the only 2 forces are gravity, which is a conservative force. That will not change my total energy, and normal force, which is perpendicular to the motion. Okay, so this is a conservation of energy problem. So what we know is our total energy at point A has got to equal our total energy at point B. So that means that the GPE at point A plus the KE at point A has got to equal the GPE at point B plus the KE at point B. All right. Just to make a point, I know that some of these are 0. I'm going to leave them in for a minute just to point something out. All right, so the GPE at A, well, that's mg times the height at point A plus the kinetic energy, that's 1/2 m times the velocity at A squared. That's got to equal the same thing at B. So mg times the height at B plus 1/2 m times the velocity at B squared. Notice we can factor an m out of both sides of our equation, and all of these m's go away. Okay? So, as long as there are no non-conservative forces and you don't have to deal with elastic potential energy, this will always happen where your masses cancel. Okay? Be careful, though, they don't always. If you have elastic potential energy, remember, elastic potential energy is 1/2 kx squared, right? There's no m there to cancel. Okay? All right, so we can plug in our numbers. Let's see. So the height, so there we go. So g times the height at A, so that's 9.8 times 3 plus 1/2. The velocity at A is 0, right? So that squared is 0 times 1/2 is 0 equals, over here, let's see, the height at B, so that's 9.8 times 0 plus 1/2 the velocity at B squared. 1/2 the velocity at B squared. Okay, so we can solve this, right? So you're going to get, I wasn't smart enough to figure this one out. So multiply both sides by 2, and you get 58.8 equals the velocity at B squared. So the velocity at point B is going to be whatever the square root of 58.8 is, 58.8 square root gives you 7.7 meters per second. Okay, so that's kind of a standard conservation of energy problem. It was a little bit easier than many of them might be because we had these zeros, right? Okay, keep in mind that won't always happen. All right. So there you go. That's hopefully review. Last year we did a ton of these problems. I think, if I remember it, I think I usually give you the mass, but I could be wrong because I haven't gotten to that this year in my honors class, so I don't remember. All right. So let's ramp it up a little bit. Let's get a little bit more involved here. All right. So first of all, let me embiggen this so you can see what's going on here. All right. So here's the deal. So classic roller coaster example, kinda. All right. This is actually going to be quite a bit harder. All right. So it says Roy, who has a mass of 80 kilograms, is at megacolossal land. The new coaster there is completely frictionless. So we don't need to worry about a non-conservative force doing work. All right. It says Roy goes over the top of the first hill. Well, I'll make a new drawing here in a minute. But so Roy goes over the top of the first hill here, which is 50 meters tall at 10 meters a second. Question A says, how tall is the second hill, so that means over here, if his velocity at the top is 24 meters a second. So this is another basic just conservation of energy. Really not a ton new here. All right, but here's the new one. All right, question B. Assuming the bottom of the loop is on the ground, so we're going to assume that down here is a height of 0. If the radius of the loop is 15 meters, then find the acceleration of the car when Roy is a third of the way around the loop. Okay, we're actually going to do more than just find the acceleration. We're going to find the normal force on it and a whole bunch of stuff. Okay. All right. So let's start by doing part A. Okay. So I'm going to give myself a new slide here. And let's kind of redraw this, all right? So here's the roller coaster. So let's draw on the ground. That's the worst. Okay, so let's call this point, let's call this the top, and we'll call this H for hill, all right? And so what the problem told us was that at the top, the height was 50 meters, the velocity was 10 meters a second. The problem told us that at the top of the hill, on the hill rather, here, I guess I can write out the word hill, all right, we know that the velocity is 24 meters a second, and we want to find the height, okay? So this is actually very, very similar to what I just did. The total energy, so what forces are there? There's gravity, conservative, normal force, perpendicular, total energy stays constant. So we're going to have that the GPE plus the KE at the top have got to equal the GPE plus the KE on the hill. Okay, so we're going to have M times 9.8 times the height on the hill is 50 plus 1/2 M times our velocity at the top of the hill is 10, don't forget to square it, equals M times 9.8 times the height on the hill plus 1/2 M times 24 squared. Okay, so once again, the M's cancel out, and we can solve this. So we're going to get, over here, you get 490 plus 50 equals 9.8H plus 288. And then you can solve it, okay? And the height turns out to be something that is written over here on this piece of paper, 25.7 meters. All right, so that's another just kind of straightforward conservation of energy problem. All right, now, so I guess let me just point out real quick, because this will make things a little bit easier here in a minute. So what this is telling us is that our total energy on the ride is, let's see, 490 plus 50 is 540 times M, right? If we hadn't canceled them out, I'm going to use that in a minute. So the total energy at the top is 540. Okay? All right, so that's that. All right, now, the other question, this is There's a lot going on here, all right? So buckle up. I'm being very dramatic. I'm using some weird words here in this video. All right, so here we go. So assuming the bottom of the loop is on the ground at a height of 0, if the radius of the loop is 15 meters, find the acceleration of the car when Roy is a third of the way around the loop. Okay, so let's draw this again. So here's the deal. So we've got our hill, and then there's our loop, okay? So what we know is that at the top up here, the total energy at the top of the first hill was 540 m, right? Okay, we know down here our height is 0. We know the radius of the loop is 15. So r equals 15 meters, all right? And we want to figure out his acceleration when he's a third of the way around the loop. So let's think about that. A third of the way around the loop, that's a third of 360 degrees. So that means 120 degrees around the loop, right? So this would get us to 90, right? Plus 30. So we're talking about right here, okay? So I'm going to label this. This is 30 degrees. That's going to become important, all right? So, how do I want to go about this? All right, so we're trying to find the acceleration at that point. So here's the deal. There are actually two types of acceleration here, all right? There's what we call tangential acceleration. Tangential acceleration is acceleration that is either parallel or anti-parallel to your velocity. It's basically speeding up or slowing down. All right, and then there's also centripetal acceleration, sometimes called radial acceleration, because it acts, right, your acceleration always acts towards the center of the circle along the radius, okay? So a radial acceleration is due to the change in direction. Okay, so we've got two types of acceleration here, right? Our velocity is this way, but because we're going uphill, we're going to be slowing down. Oops. We're going to be slowing down. So there's a tangential acceleration causing us to slow down, and there's a centripetal or radial acceleration causing us to change directions, okay? No significance to the magnitude of these arrows here. All right, so there's a lot going on here, all right? So I guess probably the first thing that we want to do is we should probably figure out what our velocity is, okay? So to do that, I need to know my height at that point, right? So let's see. So if I look at, I'm going to highlight up my drawing here for a minute. Okay, so I know that this radius here, let me get rid of this guy. I know that this radius here is 15. So if I look at this little triangle, 15 sine 30, that tells me this is 7.5. So now if we consider 7.5 plus 15, that means the height at that green dot is just the sum of 15 plus 7.5, which is 22.5 meters. Okay? So let's find the velocity at that point. That's probably as good a place to start as any. All right, so here's what we know. We know that the total energy at the top of that first hill is equal to the total energy at that point on the loop. So 540 m is equal to, well, let's see, the GPE at that point on the loop is m times 9.8 times 22.5 plus 1/2 mv squared. And we got to solve for v, right? Sorry, my drawing's getting a little bit cluttered here. Okay, so the m's cancel out again, solvify this, and the velocity turns out to be 25.3 meters per second. Okay, so that is my velocity at that point on the loop. Okay? So, because we're going in a circle, it probably makes some sense to write an expression for, do we want to think in, let's think in terms of force, I guess. Okay? So, our centripetal force then is mv squared over r. So we know our velocity, we know our radius, so 25 squared divided by 15 gives you 42.6. So we're going to get 42.6 m. That is our centripetal force. Okay, so let's make a new drawing of this, kind of clean things up a little bit. So once again, here's our loop. I'm just going to draw it as a circle. Okay, so what we just figured out is that our centripetal force is 42.6 m. So let's think about what forces are acting on us. So here's 30 degrees. All right, so the idea is my velocity is this way, tangent to the circle, right? In fact, let's do this. This will maybe kind of illustrate kind of what's going on here. So, how do I want to do this? Let's go back and draw in our radiuses in green. So here's our radius, right? So let's see. So if that's 30 degrees, then that means that this is 30 degrees, right? Which means that the angle that we're traveling at is this angle here, 60 degrees, right? A whole bunch of geometry there, right? Okay, so let's think about what forces there are. Well, there's gravity, right? Gravity is pulling down, all right? And unfortunately, gravity doesn't lie either. It doesn't lie in the direction of either of our two accelerations, right? So I'm going to use a yellow, but I'm going to delete it in a minute, hopefully. Let's see if I can get my smartboard to cooperate. All right, so here we go. Here's our force of gravity, right? But that doesn't lie in the direction of either of our two accelerations, right? So what we need to do is we need to find the two components of this force of gravity. So there's one component that goes parallel to the velocity, and there's one component of the force of gravity that is perpendicular to the velocity. Okay? Now, why do I think about velocity? Well, think about it. If you're moving a thing up an inclined plane, suppose we had an inclined plane that was inclined at 60 degrees, and you're sliding it up the ramp. Then your velocity would be this way, right? And we would care about our FG perpendicular and our FG parallel. Oh, so we know equations for those. Okay? So the idea is, this is huge. The idea is this FG, shoot, I cannot make a new drawing. I'm going to make a new drawing. Let's do this. Okay, so at this instant that I've got highlighted, what are our forces? Well, let's see. So there's an FG parallel causing us to slow down, and there's an FG perpendicular, which is contributing to our centripetal force, right? Because it's directed in towards the center of the circle. Okay? So FG parallel, let's see, that's mg cosine of theta, where our theta is the 60 degrees, right? Because that's the sort of the direction that we're inclined at that point. So FG parallel is cosine of theta, so times the cosine of 60 degrees. And my FG parallel is mg sine of 60 degrees. Oh, no, I've got my sine and cosine flip-flopped. Darn it. Sorry. FG parallel depends on the sine. Oh, seriously? Smartboard. Because I'm the one that made the mistake, right? So times the sine of 60, and this one's cosine of 60. Okay? And what other force is there? Well, there's probably a normal force if we haven't left the track, right? And so the idea is our normal force also needs to point inward. Okay, so let's draw in our normal force. All right. So now let's think about what we know. So let me leave this here for a minute. Let's go back a slide. All right, so look, we know our centripetal force. So our centripetal force is the result of all of our inward forces. So this plus this have got to equal this. Okay? So let's see, mg cosine 60. So 9.8 times the cosine of 60 is 4.9. So let's write this as 4.9m. Okay? And so what I know then is thank you for being patient. I hope you're being patient. All right, so what I know is my FG parallel plus my normal force. Oh, my glob. Sorry, guys. I called two things FG parallel. That's what messed me up before. This guy is perpendicular, right? Because it's perpendicular to the motion. The motion is this way, and this is perpendicular to it. Okay? So this should be perpendicular. All right. So our FG perpendicular plus our normal force combined have to work to provide our centripetal force to get this thing going in a circle. So I'm looking at my FG perpendicular is 4.9m plus some normal force is equal to my centripetal force, which is 42.6m. Right? Oh, so that means my normal force has got to be, if you subtract 4.9, you get what, 37.7, is that right? 37.7m. Okay. And finally, this guy, mg sine theta, 9.8 times sine of 60, gives us 8.48m. Oops, try again. 8.48m, 8.48m. So my final free body diagram is going to look like this. So here's your ramp, or your loop, here's Roy. So we're going to have force of gravity, which is perpendicular to the motion. That's 4.9m that way. You've got a normal force, which is, what did we say, 37.7m. And then you've got your FG parallel to your velocity, and that is the 8.48. Oh, I did it again. Why did I keep doing that? 8.48m. All right, so there's our free body diagram. So now to find our acceleration, well, there's two types of acceleration. Unpin this. Just lost my drawing. There we go. Boop, boop. So there are two types of acceleration. There's centripetal acceleration, right? We already figured that out, right? Centripetal acceleration is it was 42.6, right? Because that's where we got the 42.6m. Okay? But then there's also a tangential acceleration producing us slowing down. So our tangential acceleration is, well, it's net force tangentially divided by our mass. So that's the 8.48. I guess we could call it negative because it's against the velocity. M over m, and so you get negative 8.48 meters per second squared. So there's two types of acceleration. Tangentially, this is our acceleration. That's causing us to slow down. And then centripetally or radially, this is our acceleration, which is causing us to change direction. All right? I know you guys are going to have some questions about that. So write down your questions. That's the first thing we'll do tomorrow, if you guys remind me. Okay? All right, I'm going to stop there. How'd we do? 29 minutes. I'll take it.